Okay, we're going to start out the chapter. We're going to talk about the mean value theorem and how we can relate the average rate of change with the instantaneous rate of change. The mean value theorem right here, you will see it on the AP test. People refer to it as MVT for the mean value theorem. It is applied when these two things are true. It is important that you know these two things. First of all, your function must be continuous over a closed interval. Notice that we are equal to a and b, so x falls between a and b. And the function must also be differentiable. On the open interval from a to b, that means we are not equal at a and b. And the reason that is because you cannot take the derivative at an endpoint. If you have a function and you have an endpoint, exactly where does that derivative fall? There's lots of ways you can draw your tangent line. There are no derivatives ever at endpoints. So, if those two conditions are met, then we will set up these problems here. We will find our number c is x, in that interval between a and b, such that the derivative is equal to the secant slope. And then we will solve that. So if we're looking at this problem down here, a graph of it, if this is my function right here, this black part is the function, and these are my endpoints. The first thing I'm looking at is it is a smooth curve that doesn't have any breaks, gaps, jumps, skips. There's no corners, nothing crazy going on. What the mean value theorem says that the secant slope right here has some place with a tangent slope that is exactly equal to that. It's saying that these two red lines are parallel to each other. We're going to find the secant slope between these 2 points and set it equal to the derivative. Another example of that would be this one over on the right. Notice again that we have a function. It goes from here to here. It's a closed interval that is smooth. There's no jump, skips, breaks. Nothing crazy is going on. We have a secant slope right there. And in this case, we have two x values where my tangent is parallel to the original secant. So all three of those lines are parallel to each other. If we want to actually find it, here's an example. We have this function graphed over here. We're going from x equals 0 to x equals 2. Those are our a numbers. We're going to find the number in between those where my secant slope and my tangent slope are parallel. So first thing we do is we take our function, find the derivative of it, x cubed minus x, that's this, take the derivative of it, 3x squared minus 1. Then we have to use these 2 points here and find the secant slope. So again, f of 0 would be 0 cubed minus 0 is 0, 0 comma 0. That's the first point. And f of 2 is 2 cubed minus 2. 8 minus 2 is 6. So that gives us the point 2 comma 6. And if the conditions of the mean value theorem have been met, then we are able to apply it. So the first condition, number 1, continuous. Yes. All polynomials are continuous over all real numbers. And step number 2, differentiable. Actually, we probably should stay here from 0 to 2 on the open interval. This we should have said from 0 to 2 on the closed interval. And the answer is also yes. Why? Derivative is polynomial. Therefore, 3 dots mean therefore. The domain of the derivative is all real numbers. Now we go and we apply the theorem. We're going to take our derivative right here, 3x squared minus 1, and set it equal to the secant slope, which would be 6 minus 0 over 2 minus 0. Finishing that work, 3x squared minus 1 equals 4. Add 1s. 3x squared is equal to 5. X squared equals 5 over 3. Take the square root. X equals plus or minus square root of 5/3. Those are the C values. Which ones do we use? Only use positive square root of 5/3 because we have to be between 0 and 2. And if we go back up here, this C value right here, this is the square root of 5/3. That is where I have tangent lines that are parallel. You probably already found my mistake right here. 3x squared minus 1 equals the slope of 3. 3 plus 1 is 4. 4, these are all 4s. You could write that as 2 over the square root of 3. All of the reasoning still holds. This point right here is the square root of 4/3, which is 2 over the square root of 3. Again, only using the positive because the negative is somewhere over here, not in our interval.